Hi there, why another video of the peak frequency counter, you may ask? Here's why. See what happens when I increase the frequency to 2 MHz? About 3 weeks ago I got an email from somebody named Haim, sorry if I pronounce it wrongly, asking me about a problem he experienced while using the original firmware, not my modification. But it turned out the problem is in a part of the firmware that I never changed, so the problem occurs in my version as well. In Haim's case, his frequency counter had trouble displaying the frequencies in the 1 to 4 MHz range. Above or below worked fine. As the title of the video gives away, the problem depends on the pulse width and the symmetry of the input signal. If you use analog signals through a preamp, it's less likely to happen but still possible. My guess is that because most people use more or less symmetric signals like sine or square waves and often use preamps, the problem has not been reported more widely. Let me explain what the problem is and how it can be fixed. Here's the relevant extract out of the 180-page monster datasheet of the PIC16F628A. The design of the frequency counter uses pin RA4 configured as timer 0 as input for the frequency. This is a Schmitt-Trigger input, which means it can deal with analog inputs as long as it stays within TTL logic levels of 0 and 5 volts. So signal level is not the problem, it's the timing and the fact that the firmware does not use the built-in prescaler until the frequency exceeds about 4 MHz. The spec explains that there are some minimum time limits the signal has to be high and low to allow the PIC to detect a valid logic level change on the timer 0 input. In addition to the minimum high and low pulse width, the overall period that is high plus low must also be longer than a minimum value. All the values in the datasheet are relative to the clock cycle, which in our case is 200 nanoseconds. To make things easier, I used this value to calculate and note the resulting minimum times in orange when no prescaler is in use and in green the times with prescaler. The key fact is that without prescaler, which is the same as n of 1, either high or low pulse width must not fall below 120 nanoseconds and the sum of both must not drop below 240 nanoseconds. For comparison, with the first prescaler value n equals 2, that is divide by 2, the minimum high and low pulse width drops from 120 nanoseconds to just 10 nanoseconds and the minimum period must now be just 120 nanoseconds long. I should point out that the datasheet marks these values as characterized but not tested, so in principle these are the limits, but they are not guaranteed to be precisely these values. In fact, I found that with the same PIC, the minimum working limits were slightly different for high pulse width and low pulse width. What does this mean in practice? I did some calculations and came up with this chart, which has frequency in megahertz on the x-axis and pulse width in nanoseconds on y. I'm plotting 6 curves for duty cycles of 5, 10, 20, 30, 40 and 50%. The line for 40% is identical to the one of 60, 30% is the same as 70% and so on, because above or below 50% we're just switching whether the high or low pulse width is the limiting factor, and since both have the same minimum it makes no difference in the plot. We can see that at 50% duty factor with high and low pulses exactly equal, the frequency counter is generally in the clear, meeting the requirements, although it does get very tight at 4.2 MHz. For all other duty factors, you find an ever-increasing frequency range where the minimum pulse width is no longer met, and below 10% or above 90% duty factor, pretty much the whole range is in the bad zone. By the way, you can see the affected frequency can go quite low, with 5% duty factor down to almost 400 kHz. It really depends what duty cycle you choose to use. Theoretically, you can make 1 Hz fail if you use 100 nanosecond needle pulses, which equates to a duty cycle of 0.00001%. Clearly, there has to be a limit of what duty cycle can be considered reasonable and the frequency counter expected to work with. Now, the way it is currently implemented, it's clearly not sufficient. Even with a perfect symmetrical wave of 50% duty cycle, we are dangerously close to failure at 4 MHz, and it only takes a very modest amount of asymmetry in the signal to cause the problems Haim describes over quite a range of frequencies. We know from the datasheet that using the prescaler will fix this because it drops the required minimum times drastically. What is a prescaler and how does it do its magic trick? The prescaler in the PIC is an asynchronous 8-bit counter that is unfortunately not accessible from the outside. But there's a similar thing that I had in the parts bin, a rather ancient 7493 chip, which is a 4-bit counter of the same type. You can see it consists of 4 JK flip-flops that are wired in series. That is, the output of the first one, QA, is the clock input for the second one, and so on. At each falling edge of the clock pulse, a J-key flip-flop toggles its output from high to low or from low to high. This is shown here on the right in this somewhat idealized timing diagram. Every falling edge of the input CKA causes a change in the output QA, changes to low, changes to high, changes to low, and so on. QA is used as input to the next flip-flop, and hence we have a QB signal that looks like this. It is clear that each stage effectively divides the original input frequency by 2. So a yellow 2 MHz CKA results in a blue 1 MHz QA, a 500 kHz QB, a 250 kHz QC, and so on. Yellow and blue refer to the scope picture I'm going to show in a moment. By picking one of the outputs of the 4 flip-flops, a 7493 would allow a prescale selection of 2, 4, 8 or 16. In the PIC the counter has 8 flip-flops, so additionally devices 32, 64, 128 and 256 are also available. Asynchronous counters are simple to implement and fast, and a key feature is the edge trigger. This means the input signal can have a very different duty cycle and the output will always have exactly 50% duty cycle. I used this in my DC to AC converter, link in the description, because I needed an exact 50% duty cycle for the H-bridge. In the PIC here, the prescaler has the same effect. A completely asymmetric 2 MHz signal, for example, is converted to a 1 MHz signal with exactly 50% duty cycle. The fact that the frequency has been halved can be compensated for by doubling the measurement period in the software. To show the effect the prescaler and the PIC would have on the signal, I built this little breadboard with a 7493 binary counter. At 2 MHz on a breadboard with all the wire loops, the signal won't be very nice square waves anymore, but good enough for this demonstration. The PIC running the old firmware is fed the 2 MHz yellow signal. The blue signal is what we would see if the prescaler would have been used. It's for display only, since the prescaler in the PIC is not directly accessible and not connected to anything except the scope. At 50% duty cycle, no problems, and the high and low pulse width are comfortably below 120 nanoseconds each. At 75% duty cycle, still no problem, but we are getting close. At 80% duty cycle and with 102 nanoseconds low pulse width, the problem appears. Note that the blue trace representing prescaler output is completely unchanged despite the input duty cycle changes. At 95% duty cycle, the counter is completely lost. Back to 50% and going the other direction. 35% still working with a high pulse width approaching the minimum. 15% and the counter can no longer detect the signal properly. And of course the same at 5%. Repeating the test with the new firmware, now using the prescaler in this range. 50%, which of course still works. 75%. 80%, this is where the problem started with the original firmware. 95%, still no problem. And the same in the other direction. 35%. 15%. 5%, all working fine now, at least over this duty cycle range at 2 MHz. In the new firmware, only the really low frequencies of 100K and below are not using the prescaler and are therefore still affected by the 120 nanoseconds pulse width limit. This is this tiny sliver here, labeled range 1. But even in this frequency range, it will tolerate duty cycles down to less than 2% or more than 98%, which is plenty good enough in my book. Previously the prescaler wasn't active in ranges 2 and 3, leading to Heim's problem, but now it is. This means the required pulse width is now just 10 nanoseconds for this whole area covered by ranges 2 to 7. The prescaler, of course, does not solve everything. The higher the frequency, more and more duty cycle plot lines dive under the 10 nanosecond boundary, indicating that a signal with that duty cycle can only be measured for sure if the frequency stays below the intersection point. So 5% or 95% duty cycle signals will generally work up to 5 MHz, 10 or 90% up to 10 MHz, 20 or 80% up to 20 MHz, and so on. These are of course nominal limits based on the datasheet. In practice, the PIC allows successful measurements for some time beyond the intersection point because it's usually quite a bit better than the datasheet values, which for this limit were only characterizations anyway. For example, with my PIC I measured a 5% duty cycle successfully up to 7 MHz, 10% up to 13 MHz, but eventually Heim's problem will reoccur. You just can't change the laws of physics.
I can't change the laws of physics.
Job's done? Not so fast. So far we have just talked about the pulse width because that was the cause of the original problem. If you recall, the other criteria from the datasheet is the required minimum length of the whole period. In this graph I plotted in red the minimum period length for the different ranges as used in the old firmware. The actual period gets rather uncomfortably close at several points over the whole range. Therefore I decided to use higher prescaler values for the new firmware, which drops the minimum period length to the green plot, which stays well below the actual signal period. The highest range is a bit of an oddity. The datasheet says the minimum period is 20 nanoseconds or 240 divided by n, whichever is greater. The old firmware uses a prescaler of 16, which would translate to 15 nanoseconds or a limit of about 66 MHz. Per datasheet, that 15 nanoseconds would be 20 and the limit would be just 50 MHz. For the new firmware, I decided to give a prescale value of 32 a try, even though that calculates to just 7.5 nanoseconds and should again be replaced by 20. Hence, for this range, the red and green plot lines should really be on top of each other and exactly at 20 nanoseconds, intersecting with the period line at exactly 50 MHz, and most importantly, there should not be any observable difference between the performance of the two firmware versions. But oh boy, was I in for a surprise. Previously I had tested the highest frequency my PIC could measure, and that was 79 MHz. I added the 123 kHz just as a marker to make sure it still did all the digits correctly. 79 MHz is not bad, considering that 50 is kind of the limit according to the datasheet. But with the new firmware and that prescaler change, 99 MHz, no problem. And pushing on, it surprised even more. A0.123 MHz. Clearly nobody ever thought that was possible. The letter A incidentally is hex for decimal 10, so the first digit is actually 10, which means yes, we are seeing 100.123 MHz shown on a PIC frequency counter. And that's by no means the end of it. 101.123 and 110.123 MHz is shown as B0.123, which makes sense because 11 decimal is hex B, but that kind of display is a bit nerdy, so I decided that the new capability warrants the effort to upgrade the display conversion part of the firmware to be able to handle the extra digit needed for going beyond 99 MHz. Here is the result. I used the clone PLJ-8 frequency counter as a control. 99 MHz? No problem. 100 MHz is now shown correctly. 101 is fine. Let's speed this up a bit. Too bad that the 3 digits now needed for the megahertz means we have lost the most right kilohertz digit. That's the problem with just 5 digits. Okay, 118 megahertz seem to be just above the limit because the kilohertz are unstable. Let's go down by 1 megahertz. And yes, 117 displays stable. Wow, 117 MHz, what an upgrade from 79, when there should not be any difference according to the datasheet. Apart from the display conversion, what is actually different in the firmware, you may ask, and this table provides the answer. On the left are the different frequency ranges that the firmware has implemented. The values may strike you as odd, but trust me, there is actually a reason why these values, but I won't go into explaining them in this video. The next column shows how that range is shown on the 5-digit display using an example value. I put units behind them, but of course there is no unit display. Instead you have a blinking decimal point if you see kilohertz, but a steady one for hertz and megahertz. The latter two ranges are far enough apart, you should know what you're measuring are a few hertz or megahertz. The gray box is what the old firmware did, and the green one shows the parameters of the new firmware. The differences are highlighted in yellow. You can see I have enabled the prescaler from just over 105 kHz onwards. To compensate for the loss of resolution by the prescaler, I have increased the gate time. Of course, since the last visible digit is at best 10 Hz and at worst 10 kHz, one could argue that measuring with a resolution of 2, 4 or 8 Hz makes no difference, but it could in fact decide whether the last digit rolls over or not, and anyway I hate throwing away accuracy unnecessarily. My theory why Wolf, the original creator of the firmware, chose those values on the left instead of the ones on the right is that he favored speed over resolution. Originally his counter had just 4 digits and it was meant to show the frequency his radio was tuned to. For that application you want the counter to respond really fast when moving the tuning knob, hence the 1/4 second gate time. I think for a generic frequency counter 2 updates per second is still quite reasonable. Well, I'm sure you and the pig tortured with high frequency needle pulses sigh in relief that this video is over. The new firmware is available from my GitHub page, link in the description, or contact me by email if you don't have a programmer. Also, consider becoming a Patreon to support the channel and get early access to videos and exclusive content. The link for that is in the description as well. Thanks for watching.